Section: Introduction. In this section, we introduce the test-time reasoning ability of large language models, LLMs, as a valuable tool for tackling difficult tasks. Recently, OpenAI launched a model called O1, which uses reinforcement learning to enhance performance during test time, particularly for complex math and coding challenges. We observe that LLMs can significantly improve their responses by employing chain of thought, COT, reasoning, where they create a plan to address user queries. Our approach, named MILS, Multimodal Iterative LLM Solver, utilizes LLMs as a generator to suggest potential solutions for a task, while an off-the-shelf multimodal model acts as a scorer to assess the quality of these suggestions. The scorer's feedback is then used to refine the GENERATOR's next set of proposals, continuing this iterative process until we reach a satisfactory solution or a predetermined number of steps. We find this straightforward method to be surprisingly effective across various tasks and modalities. By combining different generators and scorers, MILS can handle tasks such as multimodal captioning, generation, editing, and multimodal arithmetic. Unlike previous methods that rely on specialized models trained on specific datasets, MILS operates without any training, demonstrating emergent zero-shot capabilities. For example, in image captioning, we use a standard Llama LLM as the generator and CLIP as the scorer. While CLIP is trained on image text data, it does not rely on curated image caption pairs like traditional captioning models. We note that existing captioning methods often require additional training on specific datasets, whereas MILS shows the ability to generalize to new tasks without such constraints. Other approaches that do not use captioning data are typically limited to specific tasks and modalities. In contrast, MILS can easily adapt to new tasks by simply changing the generator and scorer components. For instance, we can enhance state-of-the-art text-to-image (T2I) models by linking an LLM to a T2I model, allowing the LLM to act as a prompt rewriter. We demonstrate the versatility of MILS across three modalities: images, videos, and audio, and three tasks: captioning, generation, and editing. Additionally, we show that MILS can invert multimodal embeddings into discrete text without relying on gradients, unlike previous methods that convert embeddings into continuous spaces. This capability opens up new applications, such as multimodal arithmetic, where we can invert multimodal samples into text, combine them, and then use MILS's generation ability to map them back. We visualize some of these capabilities in our figures. In the related work section, we discuss how multimodal embedding spaces are typically created by gathering large amounts of paired data, such as images and text, and training encoders for each modality. These embeddings have enabled various applications, including zero-shot recognition and image generation. We utilize these embeddings to compute similarity scores across modalities, guiding our optimization process and enhancing the capabilities of LLMs. Generative models have gained traction for their ability to generalize to new tasks, often in a zero-shot manner. LLMs are particularly effective for discrete inputs like text, thanks to their extensive training on large datasets and instruction tuning with human feedback. Techniques like chain-of-thought prompting have further improved their performance on complex tasks. However, instruction tuning requires training or fine-tuning LLMs for specific tasks, while MILS operates at inference time without any training, optimizing solutions in real time. Although some recent work has utilized LLM's reasoning abilities iteratively for optimization tasks, they often lack evaluation on visual tasks or emergent zero-shot capabilities. We focus on the latter, demonstrating that MILS can generalize to entirely new tasks at test time. While prior efforts have explored this for specific modalities, MILS seamlessly adapts to various modalities and tasks, showcasing its broad applicability. Section Summary. In this section, we introduce MILS, a multimodal iterative LLM solver that utilizes large language models, LLMs, as generators to propose solutions and off-the-shelf multimodal models as scorers to evaluate these proposals, enabling zero-shot capabilities across various tasks and modalities without any prior training. Our approach demonstrates significant versatility and effectiveness in tasks such as multimodal captioning, generation, and editing, while also allowing for innovative applications like multimodal arithmetic. Section: MILs. In this section, we describe our straightforward method for tackling multimodal tasks using MILs. Since MILs does not require training, it only uses the test sample as input. Our approach consists of two main components: the generator and the scorer. The generator creates potential solutions for the task, while the scorer evaluates these solutions and provides feedback to the generator to refine its outputs. For some tasks, we can start this process with initial scores for a set of candidates. We continue this optimization until we reach a stable solution or a predetermined number of iterations. The generator's role is to produce candidate outputs that address the task at hand. It takes a text description of the task and any scores from the scorer from the previous step to inform its next set of candidates. We typically use a large language model, LLM, for the generator because of its ability to process and reason with text. The output can also include other formats, such as images, by using models like text-to-image generators. In some cases, the generator may also use the test sample directly, especially for tasks like image editing. The scorer's job is to assign a score to each candidate generated by the generator. It compares the candidates to the test sample and can be implemented in various ways, from simple image processing functions to more complex machine learning models like CLIP. The scorer ranks the candidates based on their scores and returns the top candidates to the generator. In our initial tests, we found that selecting the top candidates performed best, so we adopted that strategy. The optimization process in MILs aims to find the best candidate generation according to the scorer's scoring system. We run this process for a set number of steps or until the candidates stabilize. Depending on the task, we may start with an initial set of candidates to guide the optimization. In our experiments, we evaluate MILs against existing zero-shot methods, such as MAYACAP, particularly in the context of image captioning. We find that MILs, despite its simplicity, yields more accurate and grammatically correct captions. We will detail the generator, scorer, benchmarks, and evaluation methods for each application, followed by our key findings. Importantly, MILs operates as a test-time optimization method, demonstrating zero-shot capabilities that allow it to adapt to new tasks and modalities without needing specific training data, unlike many existing methods. For image captioning, we utilize the Llama 3.18b LLM as our generator. We create an initial set of 30,000 prompts to kickstart the optimization process, ensuring diversity by using various object categories. During each optimization step, we select the top 50 candidates based on scorer scores and convert them into prompts for the next round. We run this process for 10 steps. For scoring, we use SIG-LIP, an image-text similarity model, to evaluate the candidate captions against the test image. While SIG-LIP alone cannot generate captions, it effectively works with MILs to produce captions. We assess MILs using the MSCOCO captioning test set, which includes 5,000 images. We apply standard evaluation metrics like BLEU, Meteor, CIDR, and SPICE, focusing on Meteor and SPICE since they consider semantic similarity, which is crucial for our zero-shot approach. Our results show that MILs outperforms existing methods, including those that also use language models and CLIP-like models. While other approaches involve complex processes, MILs remains conceptually simpler and easier to implement, achieving better outcomes. We provide examples of captions generated by MILs and compare them to those from MAYACAP, demonstrating that MILs can produce accurate and grammatically correct captions without prior exposure to captioning data. Section Summary. In this section, we describe our training-free approach, MILs, for solving multimodal tasks, which utilizes a generator to create candidate solutions and a scorer to evaluate and refine these candidates iteratively. Our method demonstrates competitive performance in tasks like image captioning, achieving accurate and syntactically correct results without requiring task-specific training data. Section: Video Captioning. In this section, we discuss video captioning. We find that Mills easily adapts to videos without significant modifications. We utilize the same generator as in our image captioning experiments, along with the same initial prompts. For the scorer, we employ a vClip model that analyzes 8 frames from the video and provides a similarity score between the video and the caption. Our experiments are conducted on the MSRVTT test set, which includes nearly 3,000 videos, each lasting between 10 to 30 seconds. We present our findings in a table. Most previous video captioning research relies on training data, so we compare Mills to models trained on datasets like How-To 100M and Video CC3M, reporting their performance on MSRVTT. We use the CIDR and Meteor metrics for evaluation. Remarkably, Mills, despite not being specifically trained for video captioning, surpasses the model trained on How-To 100M in both metrics. Even when compared to the same model trained on the cleaner Video CC3M data, Mills performs better on the Meteor metric, which focuses on semantic understanding. This highlights the significance of training data for video captioning models. The competitive performance of Mills without requiring video captioning training is very encouraging. We also provide qualitative results in the appendix. Next, we explore audio captioning. Similar to video captioning, Mills transfers effectively to this task. We use the same generator as before, along with 50,000 initial audio prompts generated by a language model. For the scorer, we apply the image bind model, which integrates various modalities, including audio and text, into a shared space. We evaluate our method on the Clotho audio captioning dataset, using automatic metrics as in our previous work. Our performance is summarized in a table, showing that Mills achieves strong results compared to a similar zero-shot approach, zero caps, particularly excelling in semantics-aware metrics like Meteor and Spice. Other audio captioning methods require training on specific data, which we note in the appendix. We then discuss improving image generation using Mills. By applying Mills to a generator based on a latent diffusion model, we achieve significantly higher quality images. We illustrate the original input prompt, the output from the base model, and the results from Mills. Mills is not limited to multimodal understanding. It can also enhance multimodal generation tasks, starting with text-to-image generation. We connect a language model to a text-to-image model to produce high-quality images. We test 2 advanced models, a latent diffusion model and Flux. The language model's role is to refine the prompt for the text-to-image model, aiming to improve the image quality while staying true to the original text. Notably, this generator does not require an initial prompt set. For scoring, we use PickScore, a model that evaluates the likelihood of an image being preferred by humans based on a text prompt. We score each output from the generator and return the results. The rest of the process follows the same approach as before. In terms of style transfer, we utilize gram matrix distance as the scorer to identify the necessary edit prompt for applying a specific style to an image. For evaluation, we use the Drawbench prompt set, which contains 200 textual prompts. Given the limitations of automatic metrics in media generation, we conduct evaluations with human annotators from Amazon Mechanical Turk, adhering to the JUICE framework. We assess the generations based on quality and faithfulness to the input text, using a web interface for annotators to compare images generated by the baseline model and those enhanced by Mills. Each image is evaluated by 3 annotators, and we calculate a win percentage based on majority votes. Our human study results indicate that annotators prefer images enhanced by Mills over those from the base model. We provide qualitative comparisons, demonstrating the clear improvement in aesthetic quality with Mills. We observe that Mills simplifies complex prompts and adds aesthetic details, enhancing both quality and faithfulness. While recent work shows that language model-based prompt rewrites can boost media generation, they often require a tedious process of trial and error. Mills automates and complements this process, either by refining each generation or suggesting candidate rewrites for expert prompt engineers. This capability is not easily achieved by previous methods, which typically require complex computations. MILS, as a gradient-free optimization approach, facilitates diverse applications within a straightforward framework. Section Summary. In this section, we demonstrate that MILS effectively transfers to video and audio captioning tasks, achieving competitive performance without requiring specific training on video or audio datasets. We also explore its application in multimodal generation, showing that MILS enhances text-to-image generation quality and simplifies complex prompts, outperforming baseline models in human evaluations. Section: Style Transfer. In this section, we explore style transfer, which goes beyond just generating images to include editing tasks. Specifically, we focus on creating an image that combines the content of a test image with the style of a style image. For our generator, we connect the output of a large language model, LLM, to an image generation model. Unlike previous methods, we also input the test image to ensure the content remains the same. We utilize an image editing model to produce the stylized image based on the test image and the edit prompt from the LLM. To evaluate the quality of the style transfer, we measure how similar the colors and textures of the generated image are to those in the style image. We do this by calculating the distance between gram matrices of image features from different layers of a VGG19 convolutional neural network, CNN. The lower layers help maintain the style, while the higher layers preserve the content. We use MILS to minimize both style and content losses. We present results showing that MILS can perform style transfer effectively without any prior training, even without the LLM seeing features from either the test or style images. Next, we investigate cross-modal arithmetic, which is a unique application made possible by MILS. Unlike previous methods that map embeddings to continuous image space, our approach allows us to invert these embeddings into discrete text space. This flexibility enables us to combine different modalities, inspired by ImageBind, which mapped various modalities into image embedding space. We demonstrate how we can invert both image and audio into text, combine these outputs using an LLM, and then convert the prompt into a high-quality image. The resulting image reflects the semantic concepts from both modalities. We also analyze key design choices in MILS, primarily focusing on the image captioning task. For our analysis, we randomly sample 1,000 images from MSCOCO for captioning and use a set of 200 prompts for image generation. We report metrics like clip similarity and pick score averaged over these sets. We evaluate performance over optimization steps for both tasks, noting that both the scorer output and downstream metrics improve as we optimize, converging after 10 to 20 steps. We find a strong correlation between the scorer output and downstream performance, and we visualize these results to show the effectiveness of MILS. Additionally, we assess the impact of the initial candidate set size, finding a positive correlation between the size of this set and final performance. This indicates that a diverse initial set is crucial for the generator to avoid local minima. Finally, we evaluate the size of the generator and scorer, discovering that larger models generally yield better performance, particularly with LLM scaling showing the most significant improvements.